All right, guys, it is time to prepare for our last CFA, CFA number 7. All right, guys, let's take a look at this example in which the local butcher shop gives its customers a discounted price per pound on steak based on how many pounds they buy. They pay 13 if they buy less than a pound, 12 if they buy between 1 and 2 pounds, and 11 if they buy more than 2 pounds. We want to write a piecewise function that represents this situation. A couple things to remember. You want to make sure that your constraints are correct, specifically that your inequality symbols either have an equal to or a not equal to based on the words in the question. So let's dive into this one. Piecewise functions have two parts. They have a value or an equation, and then they have a corresponding constraint that goes with them. So for the first value that a customer could be charged would be $13, and that corresponds to if they buy less than a pound. Now let's talk about less than. Less than does not include 1 pound. So when we write the inequality, we want to make sure it does not have an equal to under it. So for this first constraint, we're going to say that the value, if a customer purchases less than 1 pound, is 13. The constraint for that value is that x, when this in this case represents a pound, when the pounds is less than 1. So when it's less than 1 pound. Now the second constraint it comes to play if the customer buys between 1 and 2 pounds. So between 1 and 2 pounds does include 1 and 2. So both of those should have equal to's underneath their inequalities. And if the customer buys between 1 and 2 pounds, they're going to be charged $12. So our second value is 12, and that occurs when the customer buys between 1 and 2 pounds. And then the last value that the customer could be charged would be $11 a pound. This is the most discounted price, and that is if the customer buys more than 2 pounds. Now, more than 2 pounds does not include 2. It includes anything above 2. So when we write the constraint for the value of $11, we need to make sure the inequality does not have an equal to under it. So final constraint for the value of $11 a pound occurs when the pounds x, is greater than 2. And there you have it, guys. There's the 3 equations and their corresponding constraints for this piecewise function. All right, in this function, we are given a population mean of $57 and its margin of error, which is $11. We want to know which of the 4 choices has a possible plausible value based on the mean and the margin of error. So what you're going to do here is use the mean and calculate the range of plausible values. You're going to do that by taking the mean, in this case is $57. We want to add and subtract the margin of error, which is $11. So we're going to subtract 11 from 57, and we're going to add 11 to 57, and that's going to give us the range of plausible values. Now, when we do that, when we add and subtract 11 to 57, we get that our range is from between 46 and 68. So basically, for this question, you want to determine which of those values given falls within our plausible range of values. In this case, the only one that does is $54. All of the other ones are outside of this range. All right, back to questions related to the normal distribution. Remember, you have 2 options with these questions. You either are using the curve or you are using the calculator. One of the important things to be able to know is, when do I know how to do that? How do I know how to use the curve or the calculator? So easiest way is just to go ahead and build those numbers under the curve, or what would be the curve if you use the curve. If the numbers you're trying to find the probability for are not in those values, then that is your clue that you need to use the calculator. So let's take a look. In this case, Colorado's snowfall averages around 67 inches with a mean of 8 inches. So our with a standard deviation of 8 inches. So our mean is 67, our standard deviation is 8. Now, if we were building the curve, and I'm just going to build the numbers, I'm not going to actually draw the curve. So I'm just going to start with the mean being the absolute middle value. So we're going to say that our mean is 67 based on what's given. All right, now to get the 3 standard deviations to the right, we're going to take the standard deviation of 8 and add 8 each time until we have 3 standard deviations to the right. So doing that, we're going to do 3 standard deviations to the right first, and then we'll go to the left. So when I add 8 to 67, I get 75. When I add 8 to that, I get 83. And when I add 8 to that, I get 91. All right, now that's 3 standard deviations to the right. Now let's do 3 standard deviations to the left. So now I'm going to take 67, the mean of 67, and I'm going to subtract 8 over and over again until I get 3 standard deviations to the left of the mean. So 67 minus 8 is 59, 59 minus 8 is 51, and 51 minus 8 is, why am I having so much trouble with this? It's going to be 43. All right. Now, so there is just the numbers below the curve if I were using the curve. Now, in this first part, we want to know what is the probability that Colorado receives at least 72 inches of snowfall per year. If you take a look at our values underneath the curve, none of these values are 72. So that's my clue that I'm going to have to use the calculator to do this question. And remember, for the calculator, you need 4 things. You need your lower bound. So we need let's get a different color here. We need our lower bound. We need our upper bound. We need our mean, which is given. In this case, the mean is going to be 67 for all of these, and standard deviation is not going to change either. It's going to remain 8. So really the only thing that you need to worry about is what the lower bound is and what the upper bound is for each of these 3 situations. All right, now I'm going to go back and forth between the graphing calculators to remind you how to put these in. In the first one, we want the probability that Colorado receives at least 72 inches of snowfall per year. Now, at least implies 72 or more, all right, is basically what that's saying in words. So in this case, we want our lower bound to be 72. And we want our upper bound to be something really large. We don't have infinity, so we're just going to say it's a million. All right, so this is what we're going to put in our calculator. Now, like I said, the mean is 67, the standard deviation is 8. That's not going to change for these problems, for any of these problems. So then if we go to our calculator, maybe, if it will let me. All right, guys, so let's look at our calculator. I'm going to have it. It's weird. It makes me scroll up and down to access it, but we're going to see if we can make it work. All right, so we want to remember to get to the normal distribution where you're plugging in to find your probabilities. You're going to go to second, vars. We want option number 2 for normal CDF. In this case, we made, and I'm going to clear this, we made our lower bound to be 72. We made our upper bound to be a million. We made our mean was 67 and our standard deviation was 8. We're going to enter through all of that, and that tells us that we should have a probability of 0.266 for Colorado to receive at least 72 inches of snowfall next year. So again, we have 0.266. Let me double check I got that number right, because for some reason, yep, I'm good. All right. So for the next one, this time we want to know the probability that Colorado will receive between 54 and 77 inches of snow. So in this case, the bounds are given to us. We want our lower bound to be 54. We want our upper bound to be 77. And again, the mean stays 67. The standard deviation stays 8. So we're going to go back to second vars. We're going to go back to number 2. And I already forgot what the bounds are. They are for 54 and 77. So all we have to change here are the bounds. The mean and the standard deviation stay the same. All right, so this is going to be, gosh, man, my memory today is 54 and 77. All right, 54 and 77. Mean stays the same, standard deviation stays the same, and that gives us a much higher probability and this time of 0.842, 84.2% chance that that is going to happen. Now, in the third example, what's the probability that Colorado receives at most 60 inches of snowfall? At most implies 60 or less. All right, so in this case, 60 is our upper bound. So our lower bound is something really small. So we're just going to call it negative a million. And then our upper bound is 60. All right, so one more time, going back to our calculator, clear all this out. Second vars again, this is going to get really repetitive. All right, this time we want our lower bound to be negative a million. We want our upper bound to be 60. And mean and standard deviation stay the same. This time, lowest probability, which is 0.191. All right, guys, in this case, we're a little bit tricky. We're looking at two different dot plots that represent how many siblings teachers and students have based on a survey. Both of them have 20 participants, so 20 teachers that were surveyed, 20 siblings that were surveyed. And the way that I know that is I counted all these dots. Now, just to make sure we remember the dot plots, if I have 3 dots above 0, that means 3 people said, or 3 teachers said they had 0 siblings. If I have 3 dots over 1, that means 3 teachers said they have 1 sibling. So in this case, you're comparing the standard deviation and the mean for these two groups, which means we're going to have to calculate that. Doing this by hand would be a little time consuming, so we're going to use our lists in the calculator again and go to the stat menu and calculate those one variable statistics, define our mean and our standard deviation. We just need to make sure that our calculator, or that we're entering the correct numbers in our calculator. Now this is going to get a little, this is going to be a little hard for me to go back and forth between the calculator and these images. You just need to make sure that you correctly count the dots and they correspond to the correct numbers in the list. And also, don't forget that when you put them in your calculator, you got to tell your calculator which list you're drawing from. So I'm going to do my best to go back and forth. Hopefully it's not too confusing. Now let's do teachers first. All right, for the teachers, there were 3 teachers that said that they had 0 siblings. All right, so I'm going to, let's see, 3 teachers. I wish this would pop up like on top of my smart view. So again, I'm going to go to stat. I'm going to go edit my list. Right now there's nothing in it, so I don't have to clear it. I'm going to include the zeros just for the sake of clarity. So 3 teachers said that they had 0 siblings. Then we had 3 teachers that said they had 1. So we're going to keep going back. I'm going to do this for 1 and not for both, just so you can see. So 3 teachers said they had 1. So we're going to do 1 3 times. And then we've got 4 teachers that said they had 2. So 2 4 times. And then, like I said, this is a little time consuming. We had 3 teachers say they had 3. And then we have 2 teachers that said they had 4. Oops. And 3 that said 5. Now you guys, it would not be this time consuming for y'all because you're not having to go back and forth between screens. I think you get the point. 1 that said 6 and 1 teacher that had 6 siblings and 1 teacher that had 9. So our last 2 numbers should be 6 and 9. Now notice I have 20 numbers in my list, which I should. Now you would do the same process for the students as well. So you'd go over to list 2, or you could just do list 1 over again if you want to delete them. For the students, I'm just going to do it for the teachers so you remember the process. Now to figure out the mean and standard deviation, I'm going to go to stat again. I'm going to go to calculate this time, the one variable statistics. My first list is list 1, so I just enter through that. And it tells me that my mean is, remember X bar is your mean, my mean is 2.9 and my standard deviation is 2.26. All right, so for the teachers, my mean is 2.9 and my standard deviation is 2.26. Now, I'm not going to do that whole process over for the teachers, or sorry, for the students, but you go through the same process of creating the list and going to the stat menu to find these numbers. If you do it correctly, you should get that the mean for the students is 3.25 siblings and the standard deviation for the students was 1.76. So in this one, your three choices compare the mean and the standard deviations of the two groups. If you look at these numbers, you can see that the teachers on average reported less siblings. Theirs was 2.9, students was 3.25, and there was also a higher standard deviation among the teachers um, uh, than the students, meaning the ranges of the age of sibling or the number of siblings was a little higher for the teachers than it was for the siblings. So if you look through these choices, the one that says that the mean for the teachers is smaller and the standard deviation for the teachers is larger than that for the students is B. All right, so something from a little bit ago, we want to look at the equation of the f of x equals absolute value of x when it has been reflected over the x-axis and shifted up 5. So if it's been reflected over the x-axis, there should be a negative in the front of the function. So right away, that automatically takes out of the running c because there's not a negative in the front. That negative is in the wrong spot. We also want it to be shifted up 5. Shifts up and down occur at the end of the function. You're adding some value if it goes up. You're subtracting some value if it goes down. Since I want to go up 5, that means I need to have a plus 5 on the end of the function. The only one of the remaining 3 choices that has the correct negative in the front of the function and 5 added to the end is B. Now, you could have also verified this with Desmos. You could have graphed these functions. You could have graphed the original function, the parent function, absolute value of x, and then graphed each of these choices to see which one was, in fact, a reflection of the original over the x-axis, as well as a vertical shift up 5 based on the original parent function. But in this case, I don't really think it's necessary as long as you have a basic understanding of those characteristics of the transformational form of the absolute value of x. All right, we are calculating the z-scores for 2 different quiz scores. The mean of this particular quiz was 67. Standard deviation of this quiz was 8. We want to find 2 different things. For the first one, we want to find the z-score for a quiz that had a score of 83. So just as a reminder, the equation to calculate a z-score is that z equals the value you're looking at minus the mean over the standard deviation. All right, now remember, a z-score is telling us how far away from the mean a certain value is. So if the z-score is positive, we would expect that that score was above the mean. If it's negative, we would expect it's below the mean. So let's take a look at 6a. The value, the quiz score we're looking at is 83. So calculating that, we get that z equals 83 minus the mean score, which was 67, over the standard deviation, which was 8. If you calculate that correctly, you get 2 exactly. Now, it's positive, which jives with what we would expect because 83 is higher than the mean score of 67. So we do expect it to be positive. Now for the next one, for a quiz score of 52, just thinking ahead, 52 is less than 67. So I would expect that when I calculate it, it will be negative, which it ends up being. So again, I take my z-score is going to be the value, in this case is 52, minus the mean, which is 67. Standard deviation is still 8. When I plug that into my calculator, I get negative 1.875 for that z-score. It was negative as we expected. All right, back to the normal curve again. Fast food restaurant around the corner sells small, medium, and large sodas. The amount of soda in a median cup has a mean of 12 ounces with a standard deviation of 0.4 ounces. Assuming the amount of soda in each size is normally distributed, about 99.7% of the data falls within which two values? Now, again, we have to know, do I use a calculator? Do I use the curve? However, if you ever see there's three common percentages that we need to remember about the normal curve. Number one is that 68% of normally distributed data falls between one standard deviation from the mean. All right. 95% of the data lies within two standard deviations from the mean. And then 99.7% of the data lies within three standard deviations from the mean. So since we're trying to find the two values where about 99.7% of the data reside, we are trying to find this interval right here, those end points for that interval. So again, I'm going to build the curve. I'm not going to draw the curve. I'm just going to build those numbers at the end so that I can get those endpoints. All right, so my mean, we said, is 12 ounces. So 12 is going to be my dead center value. I'm going to add 0.4 to get to the right 3 times to get 3 standard deviations to the right of the mean, and then I'm going to subtract 0.4 3 times to get 3 standard deviations to the left of the mean. So let's do to the right of the mean first. If I add 0.4 to 12, I get 12.4. If I keep adding 12.4, that's going to give me 12.8, and one more time, that's going to give me 13.2. All right, this right here is 3 standard deviations from the mean. This would be 2, and this would be 1. Okay, we're going to do the same thing to go to the left. Now this time, since we're going to the left, we're going to subtract 0.4 to get the numbers to the left of the mean. So the 1 standard deviation to the left is 11.6. Subtract 0.4 again, that gives me 11.2. Subtract 4 one more time, that gives me 10.8. Now again, we've got 3 standard deviations to the left of the mean here, 2 to the left of the mean here, and 1 to the left of the mean here. So if we're looking for 99.7% of the distribution of the data, we're looking between 3 standard deviations. So we are going from here to here. And those values are 10.8 and 13.2, and that would give us C as this answer. Here we're looking at student A and student B who are running for president. A poll of the student body shows that student A is winning with 52% of the votes. However, there's a margin of error of 5.1%. Which of the following is true? Anytime, for the sake of this class, you see that margin of error, automatically you should think that you need to calculate that range of plausible values, and then from there you can answer the question. So my population for mean for this example is 52%. With a margin of error of 5.1. So we're going to add and subtract 5.1% to 52% to get that range of plausible values. If you do that, you get that your range is 46.9 to the left and all the way to 57.1 to the right. All right, now, if you notice, this range of values on the left end right here, that includes values that are less than the majority. So if this student who is winning right now actually got on the lower end, the 46, 47, 48%, that student actually would lose. So for that reason, you cannot really predict that student A is going to win, because it is possible that he won't based on the margin of error. So the answer to this question is D. Student A cannot be predicted solely because of that margin of error. That margin of error includes values that would predict that he actually would lose. Still looking at a poll. This poll shows candidate A is ahead of candidate B 57% to 43% with a margin of error of plus or minus 6%. Does the poll accurately indicate which candidate is going to win? Now this one is worded a little differently. Notice we have two percentages. Those percentages represent each candidate. When we have two percentages or more than two, we have to look at that margin of error for both of them and look to see if there is an overlap. If there is an overlap, it is not an accurate poll and we cannot use it to predict. If there is not an overlap, then we are good and we can use this poll to predict which candidate is going to win. So let's find the range of values for each candidate first. So candidate A has 57%. Both of them have a margin of error of 6%. So candidate A has a range of possible values of if I subtract 6, I'm going to get 51. If I add 6 to 57, I'm going to get 63. Now, if we do the same for candidate B has 43% of the votes, also with a 6% margin of error. So if I subtract 6 from 43, I get 37. If I add 6% to 43, I get 49. Now the question is there an overlap? I've done this before. I sort of like to put it on a pseudo number line. So let's look at candidate A. So candidate A is from 51 to 63. Candidate B is from 37 to 49. Notice that 49, its highest value, is still lower than the lowest value for candidate A. So if I sort of offset it a little bit, for candidate B, that candidate's range is 37 to 49. Notice that there is no overlap there. There are no percentages in candidate A that are also in candidate B. So for that reason, we can use this poll to predict who is going to win. So in this case, we're going to say that yes, we can use it to predict because there is no overlap in the percentages. Here we're going to determine the equations and intervals for the piecewise function as well as calculate the average rate of change over the interval 2 to 3. So let's look at the piecewise function first. Our first piece is x plus 3. So this is a line that would cross the y-axis at 3. That's going to be this red piece right here. If I kept using a slope, which in this case the slope is 1, we typically don't write the 1, but this is in slope-intercept form. There is a 1 there, so this slope is 1. If I continue to do a slope of 1 here to use more points, notice that that function is going to cross at 3. So that's the first piece. Now this function, if you look at this piece, there is an open circle there on that endpoint, which is at x equals -2. That means the inequality for this constraint should not have an equal to, because that is an open circle. Also, if I like doing sort of little dotted lines for this particular piece that stops at -2, all of that piece is to the left of -2, which means its inequality should be x is less than -2. Again, I should not have an equal to under that piece because it has an open circle on that right end. So I am looking in these choices, I am looking for a piecewise function that has x plus 3 less than -2. Now, lucky for me, if I look at all of these choices, and I don't think we did this on purpose, but using your test taking skills, if you look at all of the pieces for x plus 3 and all of the constraints, every single one of them except A has inequalities that are incorrect. This one should be less than, not less than or equal to. This one should be less than, and this one also should be less than for them to be considered. So I actually knocked all 3 of them out just by finding that first piece. So in this case, the A is the correct answer. And we could go through it just to verify that you understand why all of it is correct. So let's just look at the second piece, which is the absolute value that's been flipped down and moved up 5. So that is this blue piece here. All right, that one is going from -2 to 3. I should have a not equal or an equal to on the left and not equal to on the right, which I do right here. between -2 and 3. And the next -4 is that green piece. This one has a closed dot at 3 and then goes to the right. All right, so that one should be x is greater than or equal to 3, which is correct here. So our answer for part A is A. Now to determine the average rate of change, remember this is just slope. All right, we can calculate slope by counting if it's a line, or we can, for any equation, we can, or function, we can estimate it by using the slope formula, which is that the slope is equal to y2 minus y1 over x2 minus x1. Now, I told my students to just, if it's a line, they can just count it, but it's possible that maybe you forget how to count, or that's not the method you prefer, in which case you can use the slope formula. If you do choose to use the slope formula, first of all, we need to make sure that we're using the right piece. So let's figure out where that's going to be. All right, here is x equals 2. Let me use a different color. Here is x equals 2. Here is x equals 3. We're looking for this piece right here, which is the absolute value function. But remember, absolute value functions have two different slopes depending on which side of the function you're looking at. We're looking at the side that has the negative slope. So be careful if you're counting. You need to count in the right direction. So if you pick any 2 points, so let's say I'm just going to come up here just so it's not confusing. So any 2 points on this piece right here have the same slope. So I'm just going to pick this point and this point. To get from here to here, I have to go down 1, which is negative, over 1 to the right, which is positive. Negative, positive makes a negative. So this has a -1 slope. Or I could pick 2 points. In this case, since we're doing between 2 and 3, I'm going to pick the point that's at 2. I'm going to pick the point that's at 3. The one point is 2, 3. So over 2 up 3, that's that left point. The other point, so this would be x1, y1. The other point was 3, 2. That was the second point to the right. This would be x2, y2. If you put it into the equation, into the slope equation, you're going to get that the slope is -1 as well, just as we got when we counted, but let's just double check. So y2 is 2, minus y1 is 3. Over x2, which we're saying is 3, minus x1, which is 2. That gives me -1 over 1, which is in fact -1. So in either case, whether you count it or whether you put it into the formula, you're getting that the average rate of change between the interval of 2 to 3, that piece number 2, is -1. All right, solving logs. Just remember a couple of things. When you are solving, most of the times you're converting unless we can use that nice property that we're actually about to going to use in this first part, 11a. You're either converting, or if you can get the logs to be the same on both sides, you can disregard the logs and just make sure that what you're taking the log of is the same. So let's look at the first one. We've got log base 3 of x minus 1 plus log base 3 of 5 equals log base 3 of 2x minus 1. Now remember, you cannot have more than one log on a side. So in this case, I have to condense into one log. Since we're adding them, I'm going to condense it as a product. So doing that, I've got log base 3 of x minus 1 times 5. I'm going to put the 5 in the front just because we usually put coefficients in the front. And the right stays the same. It's still log base 3 of 2x minus 1. Now, it's really nice now because they both have a log base 3 on each side. So they don't really cancel out. We're just disregarding them because we want these two things to be equal. The logs are already equal. We just need to make sure that this equals that. So we need to make sure that, I'm going to go ahead just for the sake of ease, I'm going to go ahead and distribute that 5. We need to make sure that 5x minus 5 is equal to 2x minus 1. Now we're just moving things around to solve for x. So I'm going to move all at the same step. I'm going to move this 2x by subtracting to the left, and then I'm going to move this -5 by adding 5 to the right. All right, that's going to cancel that, cancel that. That's going to leave me with 3x equals 4. And if I divide by 3 on both sides, that gives me that x equals 4/3. Now you would plug it back in to see if it is a viable solution, meaning you cannot take the log of a negative number. So if I plug this in and I'm taking the log of a negative number, then it is not a solution. However, you can go ahead and trust me in saying that if I plug in 4/3 either here or here, I'm not going to be taking the log of a negative number, and it is a fine solution. Now, in this second example, we're not going to be able to get this nice case like we did here where we can disregard the logs. We're going to actually have to convert in this one. So I am actually solving an equation using a natural log. I do have 2 on the left-hand side, so I am still going to have to condense just like I did before. This time, however, when I condense, I have to condense it into a quotient because it is the difference of 2 natural logs. So rewriting it in its condensed form, I've got the natural log on the top should be the x plus 4 because it was the positive term. The bottom should be the 5 because that term, the natural log of 5 was negative, and it equals 7. Now at this point I can convert because there's nothing left to move. I've got the natural log by itself. I do need to remember that the base of a natural log is e, so when I convert, I do it right. Remember, we start with the base and then go towards the equal sign. So the base of my exponential is going to be e raised to the 7 equals all of this equals x plus 4 over 5. Again, that's e raised to the 7 equals x plus 4 over 5. Now we just start moving. I need to get that 5 out of the denominator, so I'm going to multiply by 5 on both sides. That's going to give me 5e to the 7th equals x plus 4. Last step, subtract 4 from both sides. All right, and that gives me 5e to the 7th minus 4 equals x. I'm okay with you leaving that as an answer. That is the exact answer. However, you can approximate it to a decimal if you put this into your calculator. That is approximately 5,479.2. Either one is fine. All right, now we're expanding logs. Remember, with expanding logs, you always simplify the inside first. So that has got to be simplified first. There are actually 3 things I can do here. I can reduce the fraction 4 over 2. I can reduce the x's by 1 since there's 3 on the top, 1 on the bottom. And I can also reduce the y's by y squared because I've got 2 on the top, 3 on the bottom. So when I simplify everything, that leaves me with log, and on the inside, I now have 2x squared on the top, and on the bottom, I have y. Now I can start expanding. Remember, if it is a quotient, anything on the bottom in the denominator is going to be a negative term when I expand. Anything on the top is going to be a positive term. Now be careful here. There are actually 3 terms in this expansion. The 2 is separate from the x squared, and you also have the y. So since there's only one term or one factor in the denominator, we should only have one term that is negative. So when I expand, I've got log of 2, which is positive, it's on the top, plus log of x squared, also positive, it's on the top, minus log of y, because the y was on the bottom. Now, there's only one last thing we need to do to finish our expansion, and that is to drop any exponent down to the front as a coefficient using that power property of logs. So our final expansion is log of 2 plus 2 log of x minus log of y. All right, on the home stretch here, looking at 2 questions dealing with types of surveys as well, or studies, as well as sampling methods. And number 13, the Archer track coach is trying to determine the average time it takes his runner to complete the 100-yard, or his runners to complete the 100-yard dash. He records the start and stop times for each runner during practice. What did he perform? The key here is that he recorded the start and the stop times for each runner. They were running anyway. He simply stood on the track and recorded when they started, when they stopped, and then used that to calculate the average time it took all of the runners to complete the 100-yard dash. He did not do a survey because he did not ask them for the values. He did not do a census, again, because he didn't ask them. He did look at his entire team, but he did not ask them to give him the data for his study. However, he did observe. He sat again, he stood back, watched each runner run, recorded their start and stop times. So this should be the answer for 13. However, just let's talk about for an experiment for a second. If it was an experiment, the coach would have done something to two different groups. One group would have gotten a treatment, one would have gotten some sort of control. In this case, first of all, there is no treatment or control group, and nothing was actually done to a group or to the runner to get the data. He simply observed to get it. So it was not an experiment. And then the final problem, a college wants to estimate the average number of courses that students at the college take in the natural sciences. Registrar provides a complete list of student names along with their majors and campus or local address. Assuming they can only select 100, which of the following samples should produce the best estimate? Choice 1, or choice A, randomly select 100 fourth-year students and look at their courses. Problem here is they're only looking at fourth-year students. They're not looking at first through third-year students or even after fourth if they're taking more than 4 years. So it's highly biased towards 1 year of student. Choice B, randomly select 25 students from one of the 4 residency halls and look at their courses. So the key here is one of the 4. Now this is an example of a cluster sampling method. They're randomly putting them into groups. The groups in this case are the halls, and then they're randomly taking 25 from each group. So this is a clustering sample method. All right, choice C, randomly select 100 students from the complete list of students and look at their courses. So in this one, all they are doing is randomly selecting students from an entire roster, all right, from all students. This would be simple random. And then last, randomly select the same number of students from each major. Again, we're putting into groups and we are taking a random sample from each group. All right, this would be stratifying. All right, and the first one really is just bias. It just has high bias, like I said, because they're only looking at fourth-year students. So if you compare these 4 different methods, the clear winner is simple random. If you remember back from the lesson for this topic, simple random is the most accurate way to sample data if you can.